Hi, this is Database Normalization Lesson.
In this lesson, several topics will be covered. Data anomalies, types of dependencies in DBMS, normalization guidelines, first normal form, 1NF, second normal form, 2NF, third normal form, 3NF, Boyce-Codd normal form, BCNF, fourth normal form, 4NF, fifth normal form, 5NF. Anomalies are caused when there is too much redundancy in the databases, that poorly planned, unnormalized databases where all the data is stored in one table, a flat file database. There are three types of data anomalies: insertion anomalies, deletion anomalies, and update anomalies. In insertion anomalies, adding data is not possible unless another piece of unavailable data is also added. In deletion anomalies, a record of data can legitimately be deleted from a database, and the deletion can result in the deletion of the only instance of other, required data. In update anomalies, incorrect data may have to be changed, which could involve many records having to be changed, leading to the possibility of some changes being made incorrectly. This is an example of the situation happen in insertion anomalies. Consider the relation as shown in the slide. Project information cannot be inserted unless an employee is assigned to it. Conversely, employee information cannot be inserted until employee is assigned to a project. This is an example of the situation happen in deletion anomalies. Consider the relation as shown in the slide. When a project is deleted, it will result in deleting all the employees who work on that project. Ultimately, if an employee is the sole employee on a project, deleting that employee would result in deleting the corresponding project. This is an example of the situation happen in update anomalies. Consider the relation as shown in the slide. Changing the name of project number 1 from projects to computerization may cause this update to be made for all 100 employees working on project number 1. Dependencies in DBMS is a relation between two or more attributes. There are 5 types of dependencies, namely, functional dependency, fully functional dependency, transitive dependency, multivalued dependency, partial dependency. Throughout this lesson, we will use the term prime attribute that referred as an attribute that is member of the primary. In functional dependency, if the information stored in a table can uniquely determine another information in the same table, then it is called functional dependency. Consider it as an association between two attributes of the same relation. If P functionally determines Q, then we write P determine Q. For example, table employee shown in the slide shows that the emp name is functionally dependent on emp ID because emp name can take only one value for the given value of emp ID. We then write emp ID determine emp name. We say that an attribute is fully functional dependent on another attribute if it is functionally dependent on that attribute and not on any of its proper subset. For example, an attribute Q is fully functional dependent on another attribute P, if it is functionally dependent on P and not on any of the proper subset of P. Let us see an example given in the slide, T. Here relations states that emp ID, project cost determine days. However, it is not fully functional dependent. Whereas the subset emp ID, project ID can easily determine the days spent on the project by the employee. This summarizes and gives our fully functional dependency. That emp ID, project ID determine days. A functional dependency is said to be transitive if it is indirectly formed by two functional dependencies. For example, X determines Z is a transitive dependency if the following 3 functional dependencies hold true. X determine Y. Y does not determine X. Y determines Z. Note, a transitive dependency can only occur in a relation of 3 or more attributes. This dependency helps us normalizing the database in 3NF, third normal form. Let's take an example to understand it better. The table shown in the slide shows that book determine author. If we know the book, we knows the author name. Author does not determine book. Author determine author underscore age. Therefore, as per the rule of transitive dependency, book determine author underscore age should hold. That makes sense because if we know the book name, we can know the author's age. When existence of one or more rows in a table implies one or more other rows in the same table, then the multivalued dependencies occur. If a table has attributes P, Q, and R, then Q and R are multivalued facts of P. It is represented by double arrow as shown in the slide. Let's take an example to understand it better. In the table, we can see students Susanna and Peter have interest in more than one activity. This is multivalued dependency because course of a student are independent of activities that are dependent on the student. The previous relation violates fourth normal form in normalization. To correct it, divide the table into 2 separate tables and break multivalued dependency as shown in the slide. This breaks the multivalued dependency and now we have 2 functional dependencies. Student name determine course discipline. Student name determine activities.
Partial dependency occurs when a non-prime attribute is functionally dependent on part of a candidate key. The second normal form, 2NF, eliminates the partial dependency. Let us see an example. In the student project table, we have partial dependency. Let us see how. The prime key attributes are student ID and project no, and student ID equal to unique ID of the student. Student name equal to name of the student. Project no equal to unique ID of the project. Project name equal to name of the project. As stated, the non-prime attributes i.e. student name and project name should be functionally dependent on part of a candidate key, to be partial dependent. The student name can be determined by student ID, which makes the relation partial dependent. The project name can be determined by project no, which makes the relation partial dependent. Therefore, the student-project relation violates the 2NF in normalization and is considered a bad database design. To remove partial dependency and violation on 2NF, decompose the tables into 2 student project and project. Normalization is the process of decomposing unsatisfactory bad relations by breaking up their attributes into smaller relations. Normal form is the condition using keys and FDS of a relation to certify whether a relation schema is in a particular normal form. Let's move to the Normalization Guidelines. Guideline 1. Informally, each tuple in a relation should represent one entity or relationship instance. Applies to individual relations and their attributes. Attributes of different entities, employees, departments, projects, should not be mixed in the same relation. Only foreign keys should be used to refer to other entities. Entity and relationship attributes should be kept apart as much as possible. Bottom line, design a schema that can be explained easily relation by relation. The semantics of attributes should be easy to interpret. This is a simplified company relational database schema. Guideline 2. Design a schema that does not suffer from the insertion, deletion, and update anomalies. If there are any anomalies present, then note them so that applications can be made to take them into account. Guideline 3. Relations should be designed such that their tuples will have as few null values as possible. Attributes that are null frequently could be placed in separate relations, with the primary key. Reasons for nulls. Attribute not applicable or invalid. Attribute value unknown, may exist. Value known to exist, but unavailable. Bad designs for a relational database may result in erroneous results for certain join operations. The lossless join property is used to guarantee meaningful results for join operations. Guideline 4. The relations should be designed to satisfy the lossless join condition. No spurious tuples should be generated by doing a natural join of any relations. Spurious tuples. There are two important properties of decompositions: non-additive or losslessness of the corresponding join. Preservation of the functional dependencies. Note that property A is extremely important and cannot be sacrificed. Property B is less stringent and may be sacrificed. Normalization relations 2NF, 3NF, BCNF are based on keys and FDS of a relation schema. 4NF is based on keys, multivalued dependencies, MVDs. 5NF is based on keys, join dependencies, JDS. Consider the given relation. Now we will normalize using normal forms. A database table is said to be in first normal form if it contains no repeating fields or columns. The process of converting the unnormal form table into first normal form is as follows. Separate the repeating fields into new database tables along with the key from the unnormalized database table. The primary key of new database tables may be a composite key. 1NF of previous unnormal form table is as shown. We decompose the table into two. The first table consists of project_ID, project_name, manager, and project cost where project_ID is the primary key. The second table consists of project_ID, employee_no, employee_name, department_ID, department_name, and hourly_rate where the project_ID and employee_no is the composite key. A relation is said to be in second normal form if it is in first normal form and contains only those fields/columns that are functionally dependent, means the value of the field is determined by the value of another field, S, on the primary key. In second normal form we remove the partial dependencies, PD, of any non-key field. The process of converting the database table into second normal form is as follows. First, remove the partial dependencies, a type of functional dependency where a field is only functionally dependent on the part of primary key, of any non-key field. Second, if field B depends on field A and vice versa. Also for a given value of B, we have only one possible value of A and vice versa, then we put the field B into a new database table where B will be the primary key and also marked as a foreign key in a parent table. The slide shows that project_ID and employee number is the composite of the table, however there are attributes that only depend on employee number column, which is part of the key. Same goes to the hourly_rate that is also only depend on project_ID. We call this situation as partial dependency. Therefore, table decomposition is required as shown in the slide. The first table named as project_employee, consist of project_ID, employee_no, and hourly_rate. The project_ID and employee_number is the composite key of this table. The second table named as employee, consist of employee_number, employee_name, department_ID, and department_name. The employee_no is the primary key of this table. The third table named as project, consist of project_name, project_manager, and project_cost. The primary key of this table is project_ID. A database table is said to be in third normal form if it is in second normal form and all non-keys fields should be dependent on primary key, or we can also say a table to be in third normal form if it is in second normal form and no fields of the table are transitively functionally dependent on the primary key. The process of converting the table into 3NF is as follows. First, remove the transitive dependencies, TD, a type of functional dependency where a field is functionally dependent on the field that is not the primary key. Hence its value is determined, indirectly by the primary key. And make a separate table for transitive dependent field. 3NF of previous 2NF relation as shown on the slide. Break the employee table into two relations because transitive dependency exists. Where department_name depend on department_ID. The first relation is employee_no determine employee_name, department_ID. The second relation is department_ID determine department_ID, department_name. A relation, R, is said to be in Boyce-Codd normal form, BCNF, if whenever an FDXA holds in R, then X is a superkey of R. Each normal form is strictly stronger than the previous one. Every 2NF relation is in 1NF. Every 3NF relation is in 2NF. Every BCNF relation is in 3NF. There exist relations that are in 3NF but not in BCNF. Hence BCNF is considered a stronger form of 3NF. The goal is to have each relation in BCNF, or 3NF. Consider the following relationship, R, A, B, C, D. With the dependencies. A determine BCD. BC determine AD. D determine B. This relationship is already in third normal form. Keys are A and BC. Hence, in the functional dependency, A determine BCD, A is superkey. In second relation, BC determine AD, BC is also a key. But in D determine B, D is not a key. Hence we can break our relationship R into two relationships R1 and R2. Breaking table into two tables, one with A, D and C while the other with D and B. Let's take an example to understand it better. One student can enroll for multiple courses. For example, student with student. Narayan has opted for subjects, database and operating system. For each subject, an instructor is assigned to the student. And there can be multiple instructor teaching one subject like we have for database. What do you think should be the primary key? Well, in the table, student, course together form the primary key, because using student and course, we can find all the columns of the table. One more important point to note here is, one instructor teaches only one course, but one course may have two different instructors. Hence, there is a dependency between course and instructor here, where course depends on the instructor name. Two functional dependencies exist in the relation teach. FD1, student, course determine instructor. FD2, instructor determine course. 3 possible decompositions for relation teach. D1, student, instructor, and student, course. D2, course, instructor, and course, student. D3, instructor, course, and instructor, student. Out of the above 3, only the third decomposition will not generate spurious tuples after join, and hence has the non-additivity property. Testing binary decompositions for lossless join, non-additive join, property. Binary decomposition, decomposition of a relation R into two relations. Property NJB, non-additive join test for binary decompositions. A decomposition D equal to R1, R2 of R has the lossless join property with respect to a set of functional dependencies F on R if and only if either any one of the functional dependencies shown in the slide are met. If you apply the NJB test to the 3 decompositions of the teach relation, D1 gives student determine instructor or student determine course, none of which is true. D2 gives course determine instructor or course determine student, none of which is true. However, in D3 we get instructor determine course or instructor determine student. Since instructor determine course is indeed true, the NJB property is satisfied and D3 is determined as a non-additive, good, decomposition. D1 gives student determine instructor or student determine course create a spurious tuples that caused losslessness of the corresponding join. D2 gives course determine instructor or course determine courses also create a spurious tuples that caused losslessness of the corresponding join. However, in D3 we get instructor determine course or instructor determine student. Since instructor determine course is indeed true, the NJB property is satisfied and D3 is determined as a non-additive, good, decomposition.
A relation is said to be in fourth normal form if it is in Boyce-Codd normal form and primary key has a one-to-one relationship to all non-keys fields, or we can also say a table to be in fourth normal form if it is in Boyce-Codd normal form, BCNF, and contains no multivalued dependencies. The process of converting the table into fourth normal form is as follows. First, remove the multivalued dependency. Second, make a separate table for multivalued fields. Consider the example. Each row indicates that a given restaurant can deliver a given variety of pizza to a given area. The table has no non-key attributes because its only key is restaurant, pizza variety, delivery area. Therefore, it meets all normal forms up to BCNF. If we assume, however, that pizza varieties offered by a restaurant are not affected by delivery area, i.e. a restaurant offers all pizza varieties it makes to all areas it supplies, then it does not meet 4NF. The problem is that the table features two non-trivial multivalued dependencies on the restaurant attribute, which is not a superkey. The dependencies are restaurant, determine pizza variety. Restaurant, determine delivery area. These non-trivial multivalued dependencies on a non-superkey reflect the fact that the varieties of pizza a restaurant offers are independent from the areas to which the restaurant delivers. This state of affairs leads to redundancy in the table. For example, we are told 3 times that a 1 pizza offers stuffed crust, and if a 1 pizza starts producing cheese crust pizzas then we will need to add multiple rows, 1 for each of a 1 pizza's delivery areas. There is, moreover, nothing to prevent us from doing this incorrectly. We might add cheese crust rows for all but one of a 1 pizza's delivery areas, thereby failing to respect the multivalued dependency. To eliminate the possibility of these anomalies, we must place the facts about varieties offered into a different table from the facts about delivery areas, yielding 2 tables that are both in 4NF. A relations is said to be in 5th normal form if it is in 4th normal form and contains no redundant values. Or we can also say a table to be in 5th normal form if it is in 4th normal form and contains no join dependencies. The process of converting the table into 5th normal form is as follows. Remove the join dependency. Break the database table into smaller and smaller tables to remove all data redundancy.
The table's predicate is products of the type designated by product type, made by the brand designated by brand, are available from the traveling salesman designated by traveling salesman. The primary key is the composite of all 3 columns. Also note that the table is in 4NF, since there are no multivalued dependencies, 2-part join dependencies, in the table, no column, which by itself is not a candidate key or a superkey, is a determinant for the other 2 columns. In the absence of any rules restricting the valid possible combinations of traveling salesman, brand, and product type, the 3 attribute table above is necessary in order to model the situation correctly. Suppose, however, that the following rule applies. A traveling salesman has certain brands and certain product types in their repertoire. If brand B1 and brand B2 are in their repertoire, and product type P is in their repertoire, then, assuming brand B1 and brand B2 both make product type P, the traveling salesman must offer products of product type P, those made by brand B1 and those made by brand B2. In that case, it is possible to split the table into 3.
In this lesson, we have learned about informal design guidelines for relational databases, functional dependencies, normal forms, first normal form, second normal form, third normal form, based on primary keys, general normal form definitions of second normal form and third normal form, for multiple keys, BCNF, Boyce-Codd normal form, fourth and fifth normal forms,